Okay, and we're recording. All right, my name is Eric Lengyel. I am a lifetime member of Unicode and a silver sponsor of a couple different symbols that I use in my mathematical research. That has nothing to do with this talk. I'm a computer scientist and mathematician working at a small company called Terathon Software. I've been doing it since the mid-90s. I generally work on real-time rendering, game engines, 3D graphics, anything that involves the GPU. One of the products that I work on at my company is called Slug, and it does digital typography and real-time vector rendering of fonts on the GPU, the graphic processor. So today I'm going to be talking about how Slug works and what we can do with our fonts to make sure that they look amazingly good and render as fast as possible on the GPU, because it is rendering directly from the Bézier curves that define the shapes of all the glyphs. So there's a lot of calculation happening on the GPU, and you got to make sure that you're not wasting time. So Slug is used across a wide array of applications that include CAD, VR, video games, industrial modeling, even planetariums. You see a lot of game companies up here, Adobe's up here. It's become an industry standard. So making fonts that work well with libraries that render text in a vector form is important, because you've probably already used it somewhere without knowing it. Slug gets its name from the history of typography, in case you're curious. Back in the days of hot metal typesetting, newspapers would use a machine that melted an entire line of text into one piece of hot lead, and that was called a slug. And that's the primary function of this library, is to lay out lines of text. So Slug does a lot of typography and layout in addition to the rendering. I'm not really going to talk too much about this. It's mostly going to be focused on the rendering today. And I don't want this to sound like a sales pitch or anything, but I'm just trying to explain what Slug does and how it works so that the optimizations we talk about make sense later on. You understand exactly why we want to do the things that I'm talking about. So I'll show you a demo in just a second of exactly what kind of rendering you can get out of Slug, and any kind of vector rendering that works based on the same principles. But just keep in mind that behind the scenes, it also does all kinds of typography. So it's doing all kinds of layout that could involve kerning and ligatures and stacking accents on top of characters, handling emojis with all kinds of modifiers and zero-width joiner sequences, doing alternate substitution for all kinds of different things that you might have in a font, contextual substitutions, doing bidirectional layout for things like when you're mixing English and Arabic together, doing the Arabic cursive joining, vertical layout for Japanese. Sometimes there's alternate glyphs that appear when you're writing vertically as opposed to horizontally. And then paragraph layout for things like justification, doing line breaking, and handling things like optional hyphens. All right, so let's take a look at a quick demo here, just so that you know. Oops. What this can do. So this renders glyphs by sending a small number of triangles to the GPU. You can see the green outlines here. There's a small polygon between like 3 and 6 triangles for each glyph, and then a pixel shader is being run inside those triangles that actually determines what the coverage is. And since it's rendering directly from the Bézier curve control point data that defines these shapes, it never loses quality, no matter how far in I zoom in on this, within the limits of floating point precision. It will always be a nice, beautiful, smooth curve that never pixelates or becomes faceted or anything like that. There's no subdivision happening. There's no texture maps involved, no pre-computed images. Like normally, the CPU would be used to calculate or when you render a font at a specific size, normally it would be rasterized on the CPU and stored in memory somewhere, and then it would just copy those pre-rasterized images to the screen wherever a certain glyph is used. But if you're inside of a 3D environment and the camera's moving around, you don't have any fixed sizes that you're rendering your fonts at, and not even a fixed perspective. So you could be looking at text on a wall from an oblique angle like that, and you're not going to be rasterizing every single possibility as the camera moves around. So it's just not a viable way to handle this and still maintain quality. In older applications, you would render the text at a certain large size and then just scale it depending on where it appears in the 3D environment, but the quality degrades as you get further away from that one size that you rendered at. If you render it too small, it looks terrible. If you render it too large, it gets blurry or pixelated and looks terrible. So rendering directly from the original vector data solves all those problems. And then there's just a ton of different things here. Some of the fonts can get really complicated. Some of these have more than 1,000 Bézier curves per glyph, which I don't recommend using in performance critical applications, but it does work. Here's Microsoft's emoji font. We're going to take a much closer look at that. Have some fun with emoji. And even though it's not really relevant to today's talk, it does handle a subset of the SVG standard as well. So all of these diagrams here are just big SVG files being rendered on the GPU as vector graphics. Okay, and then let me switch over to a game engine here that has this integrated. In case you're curious, the 31st is a Halloween game that I've been working on forever. But, okay, so when we put this in a game environment, here I've got a camera moving around. I can get really close to text on a wall, and we still have this nice crisp outline that we would not be able to achieve if these had been rendered into a texture map. And again, it's only rendering a small handful of triangles for each of these. I think I can show you that. So just like the other demo, this is just rendering between 3 and 6, or 1 and 6 triangles per glyph. Okay, and it lets us do things like put super high quality text on very small objects. So if you have ever seen a keyboard in a video game, you get this close to it, you're not going to see this kind of quality if it's using a texture map to render the text. But since we're rendering directly from the vector data, we can do that without having to have like a giant 4,000 pixel wide texture map just for a small keyboard laying around in a game level. All right, so the main topic of this talk concerns both rendering quality and rendering speed when it comes to designing fonts. And this, what I'm showing you here is the first example of artifacts that you will notice in fonts if you blow them up to huge sizes. So the screen here is 1440 pixels in height. So we're probably rendering this letter M at somewhere around, I don't know, 5,000 or 6,000 point size. And we're seeing details that we would not normally see if we were just rendering fonts inside Microsoft Word or something. And what I wanted to point out here was how this curve right here just isn't all that smooth. And we'll see why that's happening. There's actually a bunch of extra control points in there that don't need to be there. It's making it look bad, and it's slowing it down. Because the calculations that we do on the GPU are highly dependent on how many Bézier curves are actually present in the original glyphs. Just looking at some more examples here of text being rendered on the GPU. All right, so let me go ahead and get out of there and get back to this. Okay, so I showed you that it builds a small number of triangles for each glyph, renders those on the screen, and then there's a pixel shader that does all the calculations inside there to determine how much coverage the glyph has at each pixel. And it does that by calculating a winding number, which I'll show you in just a second. It implements specific speed optimizations and solves robustness problems that existed with earlier solutions in this area. So Slug could render either just a quad per glyph, or it could render a tighter polygon like this. The reason you would want to use quads and not polygons all the time is because, well, first, the goal with rendering the tighter polygons is to cut off areas that will never have anything filled. Since we're doing a lot of calculation at every pixel, we want to reduce the number of pixels as much as possible so that we're not wasting time calculating in areas that we know are going to be empty in the end. So like for the letter P here, let's just focus on that. In the bottom right, we know that's going to be empty area, so we can make a tighter polygon here that sort of chops that off. Now, the reason we don't use these all the time is because of a kind of a quirk of GPUs that it would be better to render just plain quads at smaller sizes, because when we use more complicated polygons like this, it introduces more lines inside, more edges inside the polygon. And the way GPUs work is that it always has to render a 2x2 quad of pixels. And that's even true along the edges of a triangle. And sometimes part of that quad is going to be inside the triangle, part of it's going to be outside the triangle, and it just throws away the results that are outside the triangle. But when you have two triangles adjacent to each other, that means that along that edge, you're rendering every pixel and the quads that cover that edge twice. One for this triangle, one for this triangle, and it throws away half the results. So if you have more of these edges in here, it could end up making the GPU do more work along these edges than it saves by cutting off a few pixels at the corners here. So the performance can actually go down if you're rendering these at small sizes. So it's better to just stick with the simple quads. Okay, so the way coverage is actually calculated is by calculating a winding number. So for any pixel inside of a glyph, so okay, these represent the Bézier curves that define this letter D. Green points are on the curve, white points are off the curve, and it's a quadratic Bézier curve. So there's 3 control points, green, white, green, for each Bézier curve here. And anybody familiar with the actual math behind that? 1, 2, 3, okay, just a few people. So it's a simple combination, kind of think of it as a weighted average of these 3 points, where the weights change as you go from one point to the next, from the first point to the last point, and it just sort of traces out a curve, and the shape is determined by this center control point off the curve there. And if you want a straight line, you just put those points in a straight line. Normally, you would take the middle control point and just make it coincident with one of the endpoints, and you'll get a straight line. So the way this glyph is defined is that we have a clockwise closed contour going around the outside, and we have a counterclockwise closed contour going around the inside to make this hole inside the D. And when we want to know whether a point is inside the actual filled space of the glyph or outside, what we do, let's suppose this is the pixel that we're rendering right here, this black dot. What we do is trace a ray from that dot off to infinity and see how many times it crosses the contours. So we have to do these intersections of the contours. And if it goes from, suppose you're going along this ray, if the contour goes from left to right, as it would here, then we add 1 to the winding number. If it goes the other way, from right to left, as it would here, we subtract 1. And then here, we add 1 because it's going left to right again. And if we end up with a non-zero number at the end here, that means the pixel we started at is inside the glyph. If we end up with a 0 like we do here, that means we're outside the glyph, which could include inside of a hole inside of a glyph. And that tells us yes or no, is this pixel inside the glyph? Now, if we only did yes or no, then the glyph would be right, but it wouldn't look very good because there would be no anti-aliasing. So it actually does, I'm going to skip ahead here. It actually does a fractional coverage. It calculates a fractional coverage value if the intersections with these contours happen to be within the pixel footprint of whatever pixel that we're rendering. And that footprint will change in size depending on how large the glyph is on the screen. So if the glyph is really small, then your pixels are going to be really big. If the glyph is really big, then your pixels are going to be really small. All right, let me back up here. All right. Now, the math for doing this is actually very easy. It's just high school math. Most people who can code could implement this, but it suffers from floating point precision problems. If you implement that with the straightforward math, it works to a degree, but you're going to end up having problems. You can't really see it here. If you squint really hard, there are some streaks in here where there are pixels that are white that should not be white, where the GPU determined that a pixel was outside the glyph when it should have been inside. And the reason that happens is because floating point precision isn't infinitely precise. If we had infinitely precise computers, the basic math would work just fine. But we don't. We have 32-bit floating point numbers on our GPU, and there will be errors. Think about if a ray, one of these rays, shot straight through a control point, like this one here. It's possible, due to floating point precision problems, that the GPU will think it hit this curve and it hit this curve and will accidentally overcount. Or we could miss both curves and it'll undercount. And that is the source of errors where we get little sparkles inside the glyph as the camera moves around, or little streaks, or just other kinds of artifacts. You can even make points appear inside open holes like this that should not be lit up. So it causes all kinds of problems. I wish you could see this better. I'll have the slides on my website. And the only way to get around that is to use some clever engineering to avoid the pieces of the mathematics that introduce precision problems. And I'm not going to go over how this works, but it is possible to do it. Our product incorporates that and is guaranteed to be robust. All right, and just one more thing here. In order to render this quickly, since we want to check as few Bézier curves as possible inside the pixel shader for performance reasons, it does divide up all of the quadratic Bézier curves defining the shape of a glyph into these horizontal and vertical bands. So however many curves intersect each band is the maximum number of curves that it's going to check at each pixel, and it just determines what band each pixel is in. Now, the reason it's using these infinitely large bands instead of more subdividing further into like a grid is that pixel footprint again. As this pixel gets larger, because our font is getting smaller on the screen, if we had divided into a grid kind of like this, then we could have a pixel that covers like a large number of grid squares. And then we would have to sort out the mess of figuring out, since a curve can belong to more than one cell, we would have to sort out the whole thing about not overcounting curves that intersected more than one cell that could be in the same pixel. It's a mess, and it gets cleaned up by using these bands and having only horizontal and vertical rays, so that no matter how big the pixel it doesn't matter, because we only care how big it is or what band it's in. If the pixel can get as large as we want here, and it's not going to cause any problems. Anyway, those are details that don't really matter for the rest of the talk. It's just I just wanted to make sure that you understood what was going on in the GPU, so that the optimizations that we're going to talk about now and all the glyphs that we look at, it makes sense of why I'm telling you that things should be done the way that they're done. So first of all, as I've already mentioned, a lot of calculations happening at every pixel, so we want to make sure we minimize the number of pixels that we're drawing. The tight bounding polygons are already doing that, but fonts can be designed in such a way that the area covered by glyph outlines is reduced, and that's especially true for emoji. And we'll see some examples of that. We definitely want to eliminate any unnecessary Bézier curves, because more Bézier curves means more times the pixel shader has to loop through all those Bézier curves in order to do its calculations. So the more of those we get rid of, the faster it's going to render. And in particular, we want to minimize the number of curves in the worst band here. So the worst band here would be 7 curves. The worst band over here would be 5 curves. And the reason for that is that the GPU actually, well, I said always renders 2 by 2 quads before, but there's also larger groups of pixels that it renders in lockstep. When it's rasterizing a triangle on the screen, it'll render, depending on the hardware, either like an 8 by 4 or an 8 by 8 group of pixels, 32 or 64 pixels, and they're all running the same instructions at the same time. So if some of those pixels have to check 5 curves and some of those pixels only have to check 3 curves, the entire group is going to have to wait until the worst cases are done before new work can be assigned to those processors on the GPU. So we don't want a band here to have like 10 curves in it and all the other bands to have 4 or 5, because any group of 8 by 8 pixels that are being rendered that covers that band with 10 in it, even though part of it might have only 4 or 5 curves to look at, it's going to waste time waiting for the worst case to complete. So we kind of just want to even it out. We don't want a whole bunch of control points clustered into the same place. Okay, and there is a reason to prefer exact horizontal and vertical lines wherever it makes sense to do that. And we'll see at least one case where that's true. And the reason for that is because it costs half as much. When we're rendering these things, it shoots a horizontal ray and it shoots a vertical ray. And it combines those in order to do the final anti-aliasing. Any horizontal curve on here, like the top and bottom of the Z here, never gets inserted into horizontal bands because a horizontal ray can never hit it. Same with vertical ones. So if there were any exact vertical lines in here, they would never be put in here because the vertical ray could never hit it. Which essentially means that any exact horizontal or vertical line costs half as much to render because it's only going to be in one band instead of 2. All right, so we're going to see a lot of examples of unwanted wiggles and cusps and concavities and stray control points, especially in emoji. And there's going to be a whole bunch of special cases that I'll show you for optimizing visual appearance. So we're going to talk about performance and visual appearance here. So the biggest problem for performance, of course, is excess control points. And that M that I showed you on the wall earlier is a case of that. I've already mentioned most of this yet. We just want to reduce control points as much as possible and make sure they're not clustered, because it will hurt performance and it will, a lot of times, contribute to degraded visual appearance. Okay, and here is our first example from the Calibri font. Is it Calibri or Calibri? Calibri? Okay. For the most part, these glyphs look pretty good. But if you look at the bottom of the E here, can you see the control points there? I'll zoom in on these in a second in a demo. But there's a big clustering of control points down here. And then we kind of have the same thing going on here, but there's an asymmetry as well. Let me switch out for a second here. So this is the font import tool that we use to convert TrueType fonts into our own internal format. Okay, so here's the big cluster of control points at the bottom of the E here. it's just completely unnecessary to have this many control points to define what's really a pretty simple curve. It could probably be done with half the number of control points. And they're all clustered up in the same place. So if I turn on the vertical bands for this letter, you'll see that they're really making a large contribution to these two bands here. And it's going to slow things down. So in general, you would want to go in there and cut out unnecessary curves, because you could achieve the same exact shape with a half or a third the number of curves that we have here. Okay, and then I wanted to look at the question mark really quick, because this one, so they actually did use fewer curves on the right side, but for some reason use more curves on the left side, and it's just completely unnecessary, because they proved right here you can have the shape that you want with only 3 curves, or no, 2 curves. And instead they have 1, 2, 3, 4 over here. So that's hurting performance a little bit. All right, let me see if I can alt tab here. Yeah. Okay, and then usually I have found that when there are a lot of extra control points, you also get visual artifacts because they're done sloppily. And I'm going to speed up a little bit here because we're running out of time. I already showed you the M in that one demo. It has a bunch of extra control points up here. It actually came from Adobe's Minion Pro font. Let me bring that up really quick. So it has a very unnecessary number of control points up there. And if I turn that off, you can see how the curve is kind of wavy here. It's not smooth. So we've got some visual artifacts in addition to a bunch of extra control points that are not, they're just going to slow things down. And this side is not much better. There are fewer control points here, but it could still be a lot smoother than this.
And that's not just due to a bad conversion from the
no, these are quadratics. This came from a TTF file that had. Oh, you mean Adobe did it? It's possible. Yeah, I couldn't tell you. On a lot of these cases, I suspect. Yes, so this comes straight from the TTF file. Yeah, I do have reason to believe that some automated tools are being used to do conversions and stuff. We'll see an example in a second here where it introduces some major problems. All right. Okay, and that brings me to Comic Sans Bold. It did look like an automated tool was used to make the bold font out of the regular font, and it introduced some serious problems. Here's plain Comic Sans Bold. One of the things Slug can do is generate an outline that goes around that by expanding the Bézier curves away in their normal direction. When I did this, some very serious artifacts started showing up. And you can see these big spikes here. There's a little one on the U here, and there's some weird stuff going on with the J and the L up here, and this P right here too. So when this was investigated, what we found was that there are artifacts inside the letter. So I'm going to do this lowercase u because I know exactly where it is here. Okay, so if we zoom in really far in this, we see there's this microscopic little cusp there that showed up. This isn't in the regular font, it's only in the bold font, and a whole bunch of these show up. And it was causing the expanded outline to like spike really far down this way. And I'll try to find it for another letter here too. I'm not sure if I can find it quick enough on this. Well, those exist elsewhere too. I don't have enough time to hunt for that. But yeah, so that kind of stuff shows up. And then in some other fonts, we have problems with coincident edges. So I'm just going to go forward here. Bondschrift is a font that one of my clients was using, and it's a variable font. It's a little hard to see here, but in this font, it's good practice to not have overlapping components in a font, but this one's a variable one, and they sort of did it that way. I don't know if you can see it very well, but this vertical stroke is by itself, and then this is a separate stroke that overlaps it over here. There's some control points where it just overlaps. And the reason they did that is so that you could have like a continuous parameter for making bold and different shaped fonts out of it. But what happened here, since we have some overlap between this contour on top and this contour on top, if you zoom in, well, when that gets rendered, the anti-aliasing doesn't work out because we've got double coverage in this area right here where it overlaps. And you can see, so it's supposed to look like this, but it does look like this because it is double covering all the pixels and we're not getting as much background showing through as we should. I see this happening in emoji a lot, and it does happen in just ordinary fonts like this as well. And the way to fix that is through something called notching. So instead of having a control point, well, this control point here that belongs to the round part, they should have moved it over here and then just had like a diagonal line going in there so that when the variable font is used, this control point is going to move, and it should just move the same way for both components. And then if they didn't have a coincident edge up there, if it went diagonally this way instead, you wouldn't have this problem. They would hide it inside the font. They would still overlap, but you wouldn't have an overlap on the edge. Okay, and I'm going to have to speed up a lot here. So we're just going to get to the emoji examples. This one comes from the open source Treemoji font. If you look very closely here, you'll see that there's actually a sad face mouth in there. So what they did here was take the frowning face emoji and they just slapped this on top of there without deleting the geometry behind it. And it's very appropriate because this kind of captures my reaction when I see this kind of thing. Yeah, so we've got this piece of geometry back here that's just doing nothing. You can never see it. So it's just wasting space, wasting rendering time. So it just needs to be gotten rid of. Here's another example of that. This is from Microsoft Seago UI emoji font. So yeah, again, we've got all this geometry belonging to this mouth that was probably on another emoji, and they just didn't cut it out. You can never see any of this detail because it's always covered by the handkerchief here. It just needs to be cut off. There's a couple of control points right here. Just cut that off with a vertical line, and it'll save space and make it run faster. Here's another example where the detail from the sun behind this cloud just is never visible. We've got dozens of curves here that are just hogging up rendering time for no reason. You can just cut that off with a diagonal line going across here behind the cloud. It'll look exactly the same and render much faster and take up less space. Okay, so let's look at some excessive control points on emojis. So I'm going to be talking about Microsoft Seago font for the rest of the talk. So hopefully I'm not offending anyone in here who might have worked on these. But there's a huge number of control points here on the mouth. And if you zoom in far on that, it actually shows a whole bunch of artifacts. So again, we have a case here where there's just way more control points that we need. So it's slowing down performance and it looks terrible. And then here's another example of a very similar thing. We've got a large number of control points down here on this tassel, and it's causing this really ugly edge to show up here. Okay, and then there's cases where we have straight lines in our emoji, but for some reason, they use a lot of control points. Let me go ahead and switch out. So this is 4EF, and zoom in on this. Okay, so inside the zeros here, those are just straight lines, but we've got all of these control points stacked up there for no reason. And we could just chop them all out and just have one curve that goes one straight line that goes from here to here, and we'll chop out 1, 2, 3, well, 3 per vertical line here. And it'll just render faster because of that. It's just completely unnecessary. Okay, and then there are all kinds of problems with layer misalignment. So here's an example where we've got an orange layer on top of this yellow layer. And if we zoom in really far on this, you can see that the control points aren't lined up. And if you were to come up on this, like in a video game or something, and look at it, you'll see all of these kind of artifacts. And if you look hard enough, you'll see that these aren't lined up over here either. So all the control points are on an integer grid. Typically, for TrueType fonts, it's 2048 by 2048 for the M square. And it's particularly easy to fix these because all you have to do is snap the control points to the right locations. Here's another example where the top of this eye here just isn't quite lined up. You can see that there's some space in there. And getting back to the double coverage on the anti-aliasing. So especially in emoji, I see this a lot where there are coincident edges between layers. We've got a background layer and a foreground layer that share the same edge. You don't want to do that because you're not going to get the right amount of background showing through, and you're going to get the wrong colors along the edge. So suppose you had a pixel that covered, or an edge that covered 50% of a pixel. You want 50% of the background to show through and 50% of the top layer of the emoji to show through. But if you have a coincident edge on a bottom layer, then what you're going to end up with is 25% of the background, which is wrong, 25% of the bottom layer, and then 50% of the top layer. And you're going to see some color bleeding through there. And that, I'm going to skip ahead just a little bit here. That happens particularly in this emoji where there is something called notching used to avoid this, and they did it in this emoji, but they missed. They didn't put the control points in the right place. So you get things like this, where well, it's kind of hard to see here, but there's a dark blue background here with the red on top of it. We see some of the dark blue showing through on this edge here because there's a coincident edge there. So this is 309. I want to zoom in on this one because it's interesting. Because they tried to do it the right way here. That's what this notch is right here. So this notch belongs to this dark blue background layer. Now, had they moved this control point up to there, and the bottom one is a little closer, move that down to there, the problem would go away. But they got it a little wrong, and you probably can't see it here because I'm rendering at such high resolution, but there is an anti-aliasing problem along that edge. You can barely make it out. Okay, now here's an example where they actually did it right. So this is 3FA. I'll go look at that really quick. They have these little tiny notches in here. So this green control point belongs to the background, and actually both of them have a control point here, and that has a little notch coming in so that the background doesn't have a coincident edge with the foreground layer, and it worked out really well. Now I still have a complaint about this one. Can you see what it is? It's that these rounded parts right here are, again, detail that we can never see. So it's just wasting time. Instead of having a round endpoint there, it should just go straight across these two control points and shave off 3 curves for each of those. So 12 curves total. Okay, I got 2 more slides. I also see cases where we have 2 things coming up next to each other and there's a gap in there, or they're exactly the same and you still have coverage problems in between. It's super easy to just snap these control points together. And then finally, here's an example where they did do the right thing by instead of having like the back leg here have an edge coincident with the body of the horse here, they did extend it in here. If you can see this boxy outline here, but they went too far. We want to minimize the area, so we should cut it off like here, like really close to the boundary. And this isn't exactly a horizontal line, so it costs a little bit more than it has to. If it were an exact horizontal line, it would have half the cost. And finally, this one is the prize winner for all the problems. Let's see, 3C4. We have all kinds of crazy stuff going on here. Look at this highlight on the eye. Look how many control points are there. There's so many we can't even tell what's going on. And if I turn that off, it's just this really ugly outline. You can see there's just curves here that aren't very smooth. There's misalignments here. And then the worst part is on this hand, they actually have the sleeve kind of following the same contour here, but it's not exactly the same. So you see part of it kind of showing through here at the bottom, and they're using a massive number of control points for all of it. So it looks terrible. It's got all these control points making it render probably a tenth the speed that it could. Yeah. So some of these glyphs look great. Some of them need some work. All right, and I will leave it at that. Since I'm out of time, I'll just go here to the end.
Maybe take one question.
So I've worked as a font engineer for years and years, and I know the origin of a bunch of these problems. I can, each one I can say, oh, I know why that happened.
Yeah.
Well, isn't there a way of automating some font cleanup
I would
that will
think
just
so.
do this at scale for you?
Yeah. The thing that comes to mind first is simplifying these curves where we have this a massive number of control points here. Programs like Illustrator have functionality where it can smooth that out or approximate it with much fewer curves. If you tell it like my maximum error is 2% or whatever, it'll figure out that it can draw that within the error that you give it with like maybe 10 curves instead of 50. But we saw with the Comic Sans bold example that sometimes the automation causes problems. So if you do use automated tools, definitely check the results.
Well, thank you very much, Eric.
Yeah.